Welcome to E-Pathshala lecture series in computer science, and this course is on operating systems, and we were looking at how CPU scheduling algorithms work in the past class, and we will continue from there. And today the objectives of this class are, we will understand how different CPU scheduling algorithms work, and we will learn the difference between how preemptive and non-preemptive CPU scheduling algorithms work, and we look at the working of some CPU scheduling algorithms. So, what is CPU scheduling? When you have a number of processes that are waiting to get the CPU, one of those processes should be chosen and be given the CPU, and that is the job of the CPU scheduler. So, when there are many processes, the CPU scheduling algorithm will select one among them, and there are many such CPU scheduling algorithms. That depends on the way in which the process has been selected to be given the CPU. And in the last class, we learned how first come first served scheduling algorithm works, and we also learned how shortest job first scheduling algorithm works in the non-preemptive case. Today we will continue with that. We will learn how a preemptive shortest job first scheduling algorithm works. In a preemptive shortest job first scheduling algorithm, the shortest job process will be given the CPU, fine, as it is in any SJF, but the only thing is that whenever a high priority process, that is whenever another process with a shorter CPU burst than the currently executing process arrives, the next process will be given the CPU and the currently executing process will be preempted. Now look at this example. We have 4 processes for P1, P2, P3 and P4, and the arrival time is different for each of the process. For P1 it is 0, for P2 it is 2, for P3 it is 4 and for P4 it is 5, and each of the processes have their own burst times. Now if it is SJF preemptive, we will see how the CPU will schedule the process. Initially at time t equal to 0, there is only one process, that is there is only process P1. So, that process P1 will naturally be given the CPU, and it will be running for 2 milliseconds, and at time t equal to 2, we see that another process arrives, that is process P2 arrives, which has got a burst time of 4 milliseconds, and this process P1 has finished only 2 milliseconds of its 7 milliseconds burst time. It has to finish totally 7 milliseconds, but it has finished 2 milliseconds now. It needs 5 more milliseconds to complete its CPU burst, but at the same time there is another process P2 which needs only 4 milliseconds to finish off its CPU burst. So, what is done? This process P2 is given the CPU, and this process P1 is removed from the CPU and it is preempted from the CPU, and P2 gets the CPU now. So, P2 again runs. Now, time t equal to 4, at t equal to 4, another process arrives, that is process P3. This process P3 has got a burst time of 1 millisecond. But what about this P2? P2 has run for 2 milliseconds and it needs 2 more milliseconds to finish off its CPU burst, because the burst time of P2 is 4 milliseconds. It has completed 2 milliseconds and 2 more milliseconds are needed to finish off the CPU burst. So, we see that there is another process P3 which needs only less amount of time compared to process P2, and we preempt, and what is done? P2 is preempted and P3 is given the CPU. So, P3 is given the CPU. P3 needs 1 millisecond time to finish off the CPU burst. It finishes off the CPU burst and it is terminated, or basically P3 leaves the CPU. Now, at this time who will be scheduled? There is one process at t equal to 5 who has arrived with burst time 4 milliseconds, and P2 is still remaining with 2 more milliseconds to complete, because it has already completed 2 milliseconds. It needs 2 more milliseconds to complete, and P1 is still there which needs 4 milliseconds to 5 milliseconds to complete, because totally 7 milliseconds are needed. P1 has completed 2 milliseconds. So, 5 more milliseconds are needed by P1 to finish off its CPU burst. So, there are 3 processes now, P1 with 5 more milliseconds, P2 with 2 more milliseconds and P4 with 4 milliseconds to complete. So, of these 3 processes, which has got the shortest CPU burst, it is P2. So, P2 is given the CPU next. So, P2 is given the CPU. P2 continues to finish off its job by taking the CPU for 2 milliseconds. So, from 5 to 7 and P2 finishes off its CPU burst. Now, remaining processes are P1 and P4. P1 with 5 remaining milliseconds and P4 with 4 remaining milliseconds. Of these 2 processes of P1 and P4, the shortest is P4 and hence P4 is scheduled next. So, P4 is given the CPU. So, it runs for 4 milliseconds and it finishes off its CPU burst. And then finally, the only process remaining here is P1 with 5 milliseconds to complete, and P1 is given the CPU and P1 runs for 5 milliseconds and finishes off the CPU. So, this is how it is being scheduled. So, here you see that in preemptive SJF, whenever another job arrives with the shorter CPU burst, the currently running job is preempted and the arriving shorter job is given the CPU. Now, we will calculate the average waiting time and the average turnaround time for this scheduling. Now, first we will calculate the waiting time. What is waiting time? The amount of time a process spends after it has arrived, the amount of time a process spends before it finishes execution. So, that is waiting time. And average turnaround time is the amount of time a process at the time at which a process finishes off its entire execution. So, first waiting time, we will see that process P1, if you look at this, P1 arrives at t equal to 0, P2 arrives at t equal to 2, P3 arrives at t equal to 4 and P4 arrives at t equal to 5. Okay. Now, P1, as soon as it arrived, it got scheduled. So, initially there is no waiting time here, and then it ran for 2 milliseconds, and then from there at t equal to 2 till t equal to 11, P1 was waiting. So, during this time P1 was waiting. So, the waiting time for P1 is 0 plus this 2 to 11 is 9. So, totally for 9 milliseconds P1 was waiting. And P2, the arrival time for P2, as you can see, is 2. At t equal to 2 only P2 arrived, and it got scheduled or it got the CPU at t equal to 2 itself, and then it ran for 2 milliseconds, and then from t equal to 4 till t equal to 5, P2 was waiting. That is, for 1 millisecond P2 was waiting. So, the waiting time for P2 is 0 plus 1. And then look at P3. P3's arrival time is 4 at t equal to 4. P3 came in only at t equal to 4, and it got the CPU at t equal to 4, and it finishes off at t equal to 5. It did not have to wait at all. So, the waiting time for P3 is 0, and for P2 the arrival time is t equal to 5 and it got scheduled only at t equal to 7. So, from 5 till 7 P4 was waiting. So, it was waiting for 2 milliseconds. So, now finding the average of the waiting time of all the processes, you get the average waiting time as 3 milliseconds. Now, we will calculate the average turnaround time. First, we will look at the turnaround time of process P1. Process P1 finishes off its CPU burst only at t equal to 16, and it arrived at t equal to 0. So, the turnaround time is the time at which it finishes off its job minus the time at which it arrived. That is the turnaround time for any process. So, for P1 it is 16 minus 0. So, it is 16 for P1. For P2, what is the turnaround time? It finishes off the job at t equal to 7. it arrived at t equal to 2. So, 7 minus 2 is 5. For P3, it finishes off its work at t equal to 5 and it arrived at t equal to 4 and 5 minus 4 is 1. And for process P4, it finishes off job at t equal to 11 and it arrived at t equal to 5. So, it is 11 minus 5. So, you find the average turnaround time is 7. So, this is how you calculate the average waiting time and the average turnaround time for preemptive SJF. Now, the problem with SJF is that you need to know the length of the CPU bus and only then you can decide which process has got the shortest CPU burst and schedule based on that. But finding out the future lengths of the CPU bus of process is not possible practically. So, what can be done is we can predict the value of the next CPU burst based on how the length of the CPU bursts were in the past. So, based on the past history, try to find out what will be the length of the CPU burst in the future. It is assumed here that if the length of the CPU burst were in a similar manner, were in a particular manner in the past, then they will be only similar to that in the future. And based on that, they try to predict the length of this next CPU burst. So, here length is predicted using exponential averaging. So, you consider the nth CPU burst and it has been denoted by Tn. The actual length of the nth CPU burst is denoted by Tn. And then based on this length of the nth CPU burst, the length of the n plus 1th CPU burst or the next CPU burst is predicted. So, that is denoted using tau n plus 1 and this tau n plus 1 is defined as alpha into Tn plus 1 minus alpha into tau n. This alpha is a weight that is considered. So, some weight is given for Tn. Tn is the length of the nth CPU burst. To predict the length of the n plus 1st CPU burst, you give some weight for the just recently got over CPU burst, that is the nth CPU burst. Then you also give some weight for the past history, that is tau n. Tau n was the predicted value for the past CPU burst. So, this tau n can again even be expanded. So, if alpha is taken as 0 in the previous formula, you get the length of the n plus 1th CPU burst is equal to tau n. That is, you do not consider the recent history. That is, you do not consider the length of Tn, but you consider the length of the previous ones, Tn minus 1, Tn minus 2, etc. and so on. And if alpha is taken as 1, then tau n plus 1 will be equal to Tn. That is, you only consider the length of the just completed CPU burst or the last CPU burst. You do not consider the other CPU bursts. Okay. So, now if you expand the formula, you can find that this tau n plus 1 will be nothing but alpha into Tn plus 1 minus alpha into Tn minus 1, etc. and so on. So, depending on what weight you want to give for alpha, if you give 0.5 alpha as 0.5, then the recent CPU burst will be given 50% weightage and the remaining past history will be given another 50% weightage and so on. So, based on how you want to consider the history, you can give the weight alpha and then based on that you can predict the next CPU burst length. And that is all about shortest job first scheduling. Now, we will move on to the next type of CPU scheduling called the priority scheduling. So, in priority scheduling, what is done? Each process is assigned a priority and the priority is just a number or an integer which is given to each process, and the CPU is given to the process which has got the highest priority. So, suppose you say you are giving priorities for processes, say given priority equal to 1, priority equal to 2, priority equal to 3 and so on for processes. Say you can consider the smallest number is the highest priority, or a process with priority equal to 1 has got the highest priority and priority equal to 2 will be lower than that, etc. and so on. and this even priority scheduling can be preemptive as well as non-preemptive. In the non-preemptive case, what is done? A process with the highest priority as of now will be given the CPU, but it will be allowed to continue till its CPU burst gets over, and only then the next process will be brought in, whichever has got the highest priority among the remaining processes. But in preemptive case, whenever a high priority process is there, it will be brought in and it will be using the CPU, but when another high priority process comes in, even when this process is executing, this process will be preempted and the next process will be given the CPU. And when there are more than one process with a similar priority, equal priority, then the tie is broken by using a FCFS scheduler, using first come first served scheduler. And you can see that SGF is also a priority scheduling algorithm. The only thing is that priority here is given based on the CPU burst time. Whichever process has got a shorter CPU burst is given the higher priority. And these priorities, how are they assigned to processes? They can be either assigned internally or externally, or it can depend on internal factors or external factors. When you say internal factors, it can depend on the number of open files, it can depend on how much time each process will use and how much amount of memory a process will use, etc. and so on. Based on that, processes can be assigned priority. It can also depend on whether a process is a real-time process and so on, and if it is a real-time process, then that can be even given a high priority, etc. and so on. So, based on internal factors, it can be assigned priorities, and it can also be assigned priorities based on external factors, like depending on the importance of the process, the type of the process, say amount of funds being paid for the computer use, etc. and so on. So, based on some factor, or it can be even be a combination of factors, priority can be assigned to processes. But only problem with this priority scheduling is that, say if high priority processes keep on coming, then low priority processes will not be getting the CPU. The low priority process will have to keep on waiting. Say there is one low priority process and that is not getting the CPU at all. High priority processes keep on coming and this low priority process will stop. And how do you avoid this situation? The solution is called aging, in which as time goes on, you can increase the priority of a low priority process also. Say a low priority process was there for a long time. Say if it was there for some example, say it is there for some 10 seconds or so, then after 10 seconds you can increase the priority of that low priority process also, so that in due course of time it will also get the CPU. Now, we will see an example of priority scheduling, and this is a non-preemptive priority scheduling. There are 5 processes P1 to P5 and each one has got its own burst time, and priority is also assigned for each of the processes, and this is a non-preemptive priority scheduling. So, how is this assigned? P2 is the process here with the highest priority. I assume here that a small number, a smaller integer for the priority means it is the highest priority. So, the highest priority process here is P2. So, P2 is assigned the CPU first. So, P2 gets the CPU and it runs for an amount equal to its burst time. The burst time is 1 millisecond. So, it runs for 1 millisecond and finishes off its job. And all the processes here, they arrive at the same time. So, specific arrival times are not given for processes here, and all arrives at the same time. But among all the processes, the one with the highest priority is picked up. And after P2, the next is process P5. P5 gets the CPU next because it has got the highest priority next. Priority number 2 is for P5, and P5 uses the CPU for 5 milliseconds and it runs for 5 milliseconds till t equal to 6. Then after this, you have 2 processes now, P1 and P3, and both of them with the same priority. Priority is equal to 3 for P1 and P3. And of the 2 processes P1 and P3, one should be picked up. So, what we can do is we can break this tie using some FCFS order. Okay. So, here we assume that P1 to P5 have arrived nearly at the same time, but there is an order in which they arrive. So, we assume that P1 is arrived before P3 and hence P1 is given the CPU first. So, P1 is given the CPU, P1 has got a burst time of 10 milliseconds and it runs for 16 milliseconds till t equal to 16, and then P3 is scheduled, it runs for 3 milliseconds. So, P3 is scheduled, it runs for 2 milliseconds because the burst time is 2 and it runs till t equal to 18, and then finally the only process available is P4, it has got the least priority. Now, there is no other process and P4 is given the CPU, it runs for 1 millisecond till t equal to 19. So, now we have learnt about this priority scheduling, and then we will move on to the next CPU scheduling algorithm, that is round robin scheduling. In round robin, what is done? It is very similar to first come first served scheduling algorithm, but the only thing is that the entire CPU time is divided among the different processes that are present, and each process is given a small amount of time, small unit of time, which is called a time quantum or a time slice, and that process will run only for so much amount of time, and then it will be preempted, and then the next process will be given the CPU. And even if the process does not finish its CPU burst within that particular time, then it will be given the next round, in the next round it will be given the CPU and it can continue with its execution. So, it will go on through different rounds till it finishes off its execution. Okay. So, and this process, after its time has elapsed, it will be preempted and it is added to the end of the ready queue, and the ready queue is generally treated as a circular queue. Okay. So, one after the other, each process will get the CPU. And suppose a process is given a time quantum or a time slice, and if the CPU burst time is less than one time quantum, then the process will release the CPU voluntarily. Say suppose the time quantum is say 10 milliseconds, for each process is given 10 milliseconds, but the CPU burst time is only 5 milliseconds for a process. Then it will finish off its job by 5 milliseconds and it will release the CPU, and immediately the CPU can be given to another process. And if the CPU burst is longer than one time quantum, then the timer will go off and interrupts will be given to the operating system. There should be a context switch. The context of the currently running process will be saved and the context of the new process will be loaded into the system. And this process which currently use the CPU will be added to the tail of the ready queue, and the next process will be selected by the scheduler, whichever has to be given the CPU will be selected and it will be given the CPU. And you can see here that in a round robin system, if there are n processes in the ready queue and the time quantum is q, and then each process will get 1 by n of the CPU time and in chunks of at most q time unit at one particular time. And you can see here that no process will wait more than n minus 1 into q time units. And if you look at the performance of round robin scheduling algorithm, if the time quantum is very large, you can see that it will work very similar to a first in first out scheduling algorithm. But if it is very small, then frequently there will be switches, and there will be a switching time or little lot of time will be spent in context switch and it will be an overhead. So, now we can see how this round robin scheduling works for this example where the time quantum is taken as 20 milliseconds. Now, there are 4 processes P1, P2, P3 and P4, and the burst time for each of the process is given and the time quantum is 20 milliseconds. So, depending on whoever has arrived first, they will be given the CPU first, and here P1 is first, P1 is given the CPU first. So, P1's burst time is 53 milliseconds, but the time quantum is only 20 milliseconds. So, P1 will use the CPU for 20 milliseconds, and at t equal to 20, the timer goes off and interrupt is given to the operating system, and the context of P1 is saved and the context of the next process should be loaded. Which is the next process? The next one in the queue, that is P2. So, P2 is given the CPU and P2 can use the CPU for 20 milliseconds because the time quantum is 20 milliseconds. But now the burst time of P2 is only 17 milliseconds. So, P2 uses the CPU from 20 to 37, that is only for its burst time, only for 17 milliseconds, and at t equal to 37 it relinquishes or it leaves the CPU voluntarily. Now, t equal to 37, the next process has to be chosen by the scheduler. The next in the queue is P3 and P3 is given the CPU. So, when you are looking at this, here you can find that P3 needs a burst time of 68 milliseconds, but it will be given only 20 milliseconds because the time quantum is 20. So, it goes from 37 to 57, runs for 20 milliseconds and finishes off its job. And then from at t equal to 57, then P4 is given the CPU. P4 can again run for only 20 milliseconds and then again it will be preempted. Now, which are the processes that are remaining? P1, P3 and P4. P1 needs 53 minus 20, that is 33 more milliseconds to finish off its job, and P3 needs 68 minus 20, that is 48 milliseconds to finish off its job, and P4 needs 4 more milliseconds to finish off its job. And again it will be allotted only in a sequence P1, P2, P3 and P4, but P2 has finished off its CPU burst. So, P1, P3 and P4. So, P1 will be again given the CPU, it will run for another 20 more milliseconds. So, 40 milliseconds are over for P1 and 13 more remaining. And for P3, 40 gets over, it has to run for 28 more milliseconds, and P4 needs only 4 more milliseconds. So, from 117 till 121 it will run and finish off its CPU burst. Now, the remaining processes are P1 and P3. P1 needs 13 more, it will finish off at this point, and then P3 had already finished 40, 20 it will finish, then 8 more will be remaining, 8 more it will finish and run. So, here you can find that there is higher average turnaround time than SJF, but the response is better, that is frequently the users will get response for P1 or P3 and P4. Now, we will see how this time quantum plays a role in the time spent for context switch. So, in round robin scheduling, we see that whenever a process time slice gets over, then a context switch happens. So, what is context switch? The process state will be saved and the state of the next process has to be loaded. And if the time quantum is very small, there will be frequent switches and a lot of time will be spent on this context switch. The time that is spent on context switch is not very useful, it is only an overhead. Okay. So, in process time, if you see here, the process time is 10, the burst time is 10 and the time quantum is 12. If the time quantum is 12, then it will finish off the CPU burst within this time quantum and the context switch is 0. But if the time quantum is 6, it will not finish off, there will be one context switch that happens in between. So, there is one context switch, and if the time quantum is 1, you can see that a lot of context switches happen, and for each of the context switches, the context of the currently running process has to be saved and the context of the newly arriving process has to be loaded, and this context switch is an overhead. So, you can look at this graph that the average turnaround time, how it varies based on the time quantum. So, here we find that there are 4 processes P1, P2, P3 and P4, and the burst times of each of the process is given 6, 3, 1 and 7 respectively, and the time quantum is also given. Suppose if the time quantum is 1, we find that the average turnaround time is 11, and if the time quantum is 2, the average turnaround time is 11.5 and average turnaround time is 10.75 for time quantum equal to 3, etc. and so on. So, how does this turnaround time be affected based on the time quantum? So, here we find that if most of the processes finish off their job within the time quantum, then the average turnaround time is high. So, at t equal to, when time quantum equal to 5, we find that the average turnaround time is high. So, when time quantum equal to 5, we find that P2, P3 finishes off and you have most of P1 finished off and most of P4 also finished off. But then the time quantum is equal to 6, but it reduces, the turnaround time reduces. That is because it becomes more like FCFS, first come first served. And then time quantum equal to 6 and 7, here you find that most of the processes finish off their CPU burst, but it becomes more like FCFS, and hence the average turnaround time reduced. We have seen already earlier that for FCFS the average turnaround time is less compared to other scheduling algorithms. So, at least 50% of the job processes finish off their burst time within the time quantum, then in that case your turnaround time will be much better. So, that is all we have learnt about round robin scheduling algorithm, and today's class will give you the summary of what we have learnt in this class. We have seen that the CPU scheduling will schedule CPU among the different processes. We learnt about different CPU scheduling algorithms. We saw how preemptive SJF preempts the currently running process if another process of shorter burst arrives, and then we learnt about this priority scheduler which will schedule the process with the higher priority process first, and then we also learnt about this round robin scheduling algorithm which will divide the CPU time into time slices, and each process is given a time slice. Thank you, and the references are this and acknowledgement. Thank you.